Gauss's law is a piece of beautiful mathematics that can be used to change monstrous problems into something a bit more tasty. Let's take a look. A particle with mass causes a radial gravitational field. Gravitational fields apply a force on other objects with mass. That's why we, objects with mass, experience a gravitational pull from the Earth. The strength of this force is determined by the strength of the gravitational field. The more field lines, the stronger the field. To describe the strength of a field, we use something called flux. This is the number of field lines that go through a surface. Imagine a calm lake with a vacuum cleaner sucking up water under the surface. Water starts flowing inwards towards the source. The source is called the divergence. Let's imagine an arbitrary, non-existent shape on the surface of the lake. Gauss's law states something intuitive, that the net flux or water flowing into the shape depends on the source. It depends on the amount of water sucked into the hose. The gravitational field caused by a particle is similar to our lake. The particle is the source, or the vacuum cleaner, and the water flow is our gravitational field. What if we turn the vacuum cleaner off? Then the net flow into our shape is going to be zero. So the net water being sucked up by the vacuum cleaner is also zero. This is actually a really powerful tool in math and physics. Let's have some fun. Suppose we want to calculate the force of gravity on the moon from the Earth. But the Earth is a sphere, and it would take a lot of work to calculate the different pull from every point on the Earth. Let's imagine a non-existent sphere around the Earth, and the moon is on the surface of that sphere. According to Gauss's law, the Earth is our vacuum cleaner, and the gravitational field affecting the moon is the water flow. It's the amount of water sucked up that affects how much flows into the shape. The size of the hose doesn't actually matter. So if we pretend the Earth, our hose, was the size of a teeny point, as long as it has the same mass or water being sucked up, the gravity experienced by the moon is the same. This means we can treat the Earth as a point mass. We just proved that the actual size of the Earth doesn't affect the gravitational field around it. So the Earth could be any size, big or small, and the moon would still feel the same gravitational pull. But what if the Earth was hollow? Well, let's turn the shell of the Earth into lots of vacuum cleaners. Outside the shell, water flows as if the Earth were solid. The Earth could be totally hollow, but as long as it has the same amount of mass, you wouldn't feel a difference. What about inside the shell? There's basically no flow because all the flow cancels out. While getting closer to a side on the shell may increase the pulling force, there are a lot more vacuum cleaners pulling on the other side. Let's use Gauss's law. Imagine a sphere centered inside the Earth. Because there are no sources of gravity, no vacuum cleaners inside our sphere, the net flux from the surface of our sphere must be zero. The same amount of water that flows into our sphere has to flow out. Also, it's symmetrical, so water must all be flowing either in or out of the surface. Because the net flow is zero, this means there's actually no water flow, no gravity inside hollow Earth. That's pretty unintuitive, and you'll probably never find yourself on a hollow planet, or worse, inside of one. But next time you look at the ground and imagine a hollow shell, a point mass, or a bunch of vacuum cleaners, take a moment and marvel at the beauty of Gauss's law.